Let's talk about the nucleophilic substitution reactions in case of the square planar complexes. And the best way to start this lecture is to know what are substitution reactions actually. For that, you can see here this reaction in which the tetrachloroplatinum complex is reacting with ammonia as the ligand, resulting in the formation of this type of complex here, in which the chlorine ligand has been replaced by this ammonia ligand, right? This is what is happening here in this reaction. And moreover, if we will go on counting the oxidation state of the central platinum ion in the starting material, I mean on this side as well as on the product side, we will see that the oxidation state will come out to be +2 here in both the cases, right? And moreover, from the geometry here on the left hand side as well as on the right hand side, we can also calculate the coordination number, which will come out to be 4 here as well as even in the product side, right? So that we can say here the reactions which involve the replacement of one ligand by the another ligand, like is happening in this case. I mean chloro has been replaced by ammonia without any change in the oxidation state, which holds true for this reaction here. I mean there is no change in the oxidation number, as well as without any change in the coordination number, which is also true here, that the coordination number even it is same here before as well as after this reaction, right? So we can call this reaction as a substitution type of reaction in which the chlorine has been replaced by the ammonia as the second ligand, such that during this course of reaction the oxidation state as well as the coordination number remains same, right? Now let us have a look on different pathways which are available for these substitution reactions. The first pathway is, as you can see here, it is the oxidative addition followed by the reductive type of elimination. And after that we also have electrophilic type of substitutions, and in the last but not the least, the nucleophilic type of substitution reactions, right? And as far as this whole lecture is concerned, we will be talking about the nucleophilic substitution reactions in case of the square planar complexes, right? So once again, this whole lecture here is about the nucleophilic substitution reactions in case of the square planar type of complexes. So let us see what is there in this lecture. But before that, let me give you a brief overview about the different kinds of pathways which we have just seen on the previous slide. The first one was what it was, the oxidative addition followed by the reductive type of elimination, right? So in order to have some insight into this type of pathway, I have taken this example here in which this complex here is reacting first of all with a molecule of chlorine, I mean the molecular chlorine, resulting in the formation of this complex here, which is undergoing the elimination of a molecule of methyl chloride, finally resulting in the formation of this type of product molecule, right? And now if we count the oxidation state of the platinum here in the starting material, we will see that it will come out to be +2 in this way here I am calculating. I mean for methyl, charge is what it is, -1, and for chloride ion once again it is -1, and for this dimethyl phenyl phosphine it is what it is, 0 here, right? So when we will be calculating the oxidation state by considering these charges here, it will come out to be +2 here. In the same way, if we will be counting the oxidation state of platinum in the intermediate, it will come out to be +4 here, and finally in this product molecule it will once again come out to be +2, right? And now what is happening here is that in the first step, the addition of the chlorine is taking place, and moreover, because the oxidation number is increasing from +2 to +4, we can call this step as what? As the oxidation type of step, right? On the other hand, in the second step, you can see here the elimination of a molecule of methyl chloride is taking place, and because the oxidation number is decreasing from +4 to +2, we can call it as a reduction type of step here, right? So that I can have some name here for the first step because of this addition and this type of oxidation here in the first step, I can call it as an oxidative type of addition, which you can see here. And because in the second step elimination is taking place with reduction type of reaction, so I can better call it as a reductive type of elimination, right? And if you look here on the starting material as well as the final product molecule, you will see that in going from this to this here, what is happening, the replacement of this methyl group is taking place with our chlorine, resulting in the formation of 2-chloro here, and the oxidation state as well as the coordination number is remaining same here, right? I'm talking about this molecule here and the final product molecule. You will see that the oxidation state is +2 in the starting as well as in the final product molecule. Moreover, the coordination number is what it is, 2 + 1 + 1, it is 4 here. In the same way, even in this product molecule, it is 2 + 2, I mean 4 here, right? So we can call this reaction as what, as a substitution type of reaction, but the mechanism or the pathway is what it is, the oxidative addition followed by a reductive type of elimination. And after that, we have the second pathway, which is known by the name of electrophilic substitution. So for that, you can see here this example in which the reaction of this complex here with this electrophilic reagent, which is this HgCl2, will give us what? It is giving this type of product molecule in which this methyl has been replaced by one of these chloride, which you can see here. I have marked this chloro here in the violet color, and what is going out of the system, it is this methyl, 1 Hg and 1 chlorine from here in this way, right? And once again, if you will count the oxidation state of this platinum here in the starting material, it will come out to be +2 here, right? And even in the final product molecule, it will once again come out to be +2. And moreover, if you have a look on the coordination number, it is 4 here as well as in the final product molecule, right? So in moving from the starting to the final product molecule, there is no change in the oxidation state, there is no change in the coordination number, both remain same. But what is happening is that the methyl has been replaced by the chloride ion here, right? So this is what, this is also a type of a substitution reaction. But why we are calling it as an electrophilic type of substitution? The reason being because we are adding here some electrophilic type of reagent, that is our Hg and Cl2, right? And it is adding onto the platinum and the methyl bond in this way, resulting in the formation of this product here in this way, having square planar type of geometry, and moreover the HgCl and methyl is going out of the system, right? So once again, because we are adding an electrophilic type of reagent here, and that is being added to the platinum and the carbon of this methyl bond here, that is why we are calling it as an electrophilic type of substitution, and it is the second pathway of substitution. And now let us have a look on the last pathway, which is the main pathway of concern for this video lecture here, and this is known as the nucleophilic type of substitution, right? So in this here, you can see that when in this starting material or the complex, we will be adding this type of nucleophilic ligand here having a negative charge. It will be attacking here on the platinum and the chlorine bond, resulting in the release of the chloride ion out of the system, because it is a good leaving group, right? And what is happening here is that now the nucleophilic ligand or the new ligand, it is forming a bond with this platinum central metal ion, resulting in the formation of this complex here, right? And moreover, in this case, the platinum is present in +2 oxidation state, as well as in the final product molecule, it is present in the same +2 oxidation state, right? And moreover, the coordination number here is what it is, 4 here, as well as in this case it is what it is, 4 here, right? So the chloride here has been replaced by the nitride molecule, and there is no change in the oxidation state here as well as in the coordination number here. So we can call it as a substitution reaction, but this is surely occurring in the form of a nucleophilic attack of this ligand here onto the platinum metal in this complex here. So that is why it will be a nucleophilic type of substitution, right? So you can read from here the replacement of chloride is taking place with the help of N3 negative. The oxidation as well as the coordination number are same here, so we can broadly call it as a substitution type of reaction, and specifically it will be what? It will be a nucleophilic type of substitution. So this is an overview of the different kinds of pathways which are available for the substitution type of reactions in case of inorganic chemical reactions. We have seen the oxidative addition followed by reductive elimination, and after that the electrophilic type of substitutions, and in the last the nucleophilic type of substitution reactions, right? So after that I want to remind here that this whole lecture I am devoting to the nucleophilic substitution reactions in case of the square planar complexes, and now it is time to study the rate law for such kind of reactions, and for that we can consider this type of general nucleophilic substitution reaction in case of the platinum complexes, right? So you can see here we are having a starting square planar complex of platinum in which two normal ligands are present, which I am denoting by the L as well as L here on this side, right? And this is what? This is the leaving ligand which will be departing from our complex molecule in this product here, and this is what? This is the T ligand, or let us say this is the ligand which is present trans to this leaving ligand, right? And now you can see here that we are adding some nucleophilic ligand here, which we will be calling it by the name entering nucleophilic ligand, because it will be entering our system resulting in the formation of this kind of new product, right? So you can see here basically what is happening, that because it is a nucleophilic type of substitution, so this Y nucleophile here is replacing or substituting this X nucleophile, such that we are having this type of complex here as the final product, and the X here is moving out of this system, right? One more thing which you can observe here is that the orientation of this ligand here is same in this case as well as in this case. Moreover, the orientation of even these two ligands is same here as well as here in the final product molecule, right? And the only difference is what? That in place of X, now we are having what? We are having this new nucleophilic ligand here, that is Y. So we can call it as a retention of configuration around the central metal ion, right? So what is happening here in this type of nucleophilic substitution in a square planar complex, that the retention of configuration around the central metal ion is taking place, right? And after that the kinetics of this reaction, I mean this reaction here, it can be studied by making the concentration of the second reactant molecule to be very large, right? So you can see that we are having the concentration of the first reactant molecule, I mean this one here, and then we have the Y, that is the entering nucleophilic ligand. We have to consider the concentration of this to be present in large excess in order to study the kinetics of this reaction, so that we can write here the rate will be directly proportional to the concentration of our this complex molecule, which I have shown like this here, multiplied by the concentration of the entering nucleophilic ligand, which is Y in this case, right? And you all know from your lower classes that if the concentration of some species is present in very large excess, we have to take that concentration to be constant, right? So this is what is happening here, because we have just said that the kinetics of this reaction are to be studied by making the concentration of Y to be very large, right? So because the concentration of Y is present in very large here, so it can be taken as a constant. Now at one look from this rate law here, we can say, or it seems that this is having a second order type of reaction, because it is bimolecular in nature, right? So whatever power is present here, I mean raised to this concentration term as well as this concentration term, we can say that the molecularity of this reaction is what it is, 1 + 1 = 2 here, right? From this molecularity, it seems that it is a second order type of reaction, but in actual practice, because Y is present in large excess and its concentration is taken to be constant here, so it has to be eliminated here in the rate law, such that the rate is directly proportional to the concentration of only the starting reactant molecule or this complex here. So this reaction is not a second order reaction, it will actually be a pseudo first order type of reaction, right? So whatever reaction we are considering here, I mean this reaction, in order to find out the nucleophilic type of substitution discussion in square planar complexes, we will see that because the Y is present in large excess, so that the rate will only be dependent upon the concentration of the starting complex material, I mean this thing, and it will not be a second order type of reaction, it will actually be a pseudo first order type of chemical reaction. So that now, according to the rate law equation, we can say that the rate can also be written in this way, I mean decrease in the concentration of the starting reactant molecule with respect to time, right? And the overall rate law equation for that reaction, it can be written in this way, I mean rate will be equal to K1 multiplied by the concentration of the starting complex molecule plus K2 multiply by the concentration of the starting complex molecule multiply by that of the concentration of the entering ligand, right? That is the Y here, okay? So that we can take this term and this term, we can take it as common, and what will come in this bracket here, it will be this K1 here plus K2 multiplied by Y here, which you can see is present in this way here, right? And we know that the K1 being a rate constant, and this K2 here is also a rate constant. Moreover, the Y, which is present in large excess, so that the concentration is taken to be constant here. This whole value is what it is, actually a constant, and we can keep this constant in this way here, I mean K observed or the observed rate constant multiplied by the concentration of the initial reactant or the complex molecule, such that the final rate of this reaction will be what? It will be this K observed multiplied by the concentration of this starting complex molecule, right? And after that, if you will see, the K observed is what? From this reaction, we can say that the K observed is nothing, it is equal to K1 plus K2 multiplied by Y. So let me come back to this slide here. So once again, the K observed will be equal to what? It will be equal to K1 plus K2 multiplied by Y. And now if we draw a graph in between the K observed, which I am taking on the Y axis here, and then in between the concentration of the Y or the entering ligand, which I am taking on the X axis here. So for these different kind of entering nucleophiles, I mean different kind of Y, we may be having this type of graph here in between the K observed and the values of the concentration of Y. Okay, so you can see that for different kind of entering nucleophiles, such as the iodide ion, the cyanide ion, bromide, nitride, nitrate, as well as thiocyanate, we will be having this type of graph here. Okay, so now why we are discussing this graph here? Because we will be knowing the value of K observed experimentally as well as the concentration of Y here. So from this graph here, what we can do is we can always calculate the values of K1 as well as K2, right? And how we can do that? From the mathematical equations, we can say that the K1 values can be found from the intercepts, right? As well as the K2 values can be found from the slope of this graph here, right? So this means that when this reaction will be going on with some particular entering nucleophilic ligand, we will be having this type of graph for any of the entering nucleophilic ligand, such that from the values of the K observed as well as the concentration terms, I mean Y, we can always calculate the values of this K1 and K2 here from the intercept as well as from the slope, right? And now we know that the overall rate law equation is something like this, in which rate is equal to K1 plus K2 into Y, which is our K observed multiplied by the concentration of the starting complex molecule. And now please listen carefully that before we analyze this rate law here in terms of the nature of the reaction, it is important to find out that what type of reaction or what type of nucleophilic reaction is going on here, right? So you can see that the rate law is this here, and we are talking about this particular reaction here. In order to analyze this rate law for this reaction, it is very important to first of all understand what type of nucleophilic reaction is this one here, okay? And now in inorganic chemistry, we can have different kinds of nucleophilic substitution pathways. You can see here the substitution reactions in case of inorganic chemistry may be divided into 4 different categories. It may be associative type of reactions, it may be dissociative type of reactions, followed by interchange associative, and lastly we can also have interchange dissociative type of reactions. Once again, for this particular reaction here, if we want to study the rate law, it is very important to find out first that what is the reaction pathway of this reaction, and we have to choose from these 4 different types of pathways, because in inorganic chemistry the substitution reactions can be divided into these 4 different pathways, okay? Now what is the meaning of this thing? I mean to say that whatever values of the K1 and the K2 are there in the overall rate law equation, we need to find out that whether the K1 belongs to the associative pathway or the dissociative pathway, or is it the interchange dissociative or the associative pathway. I mean this thing here, right? And once we have confirmed that whether the K1 is following which kind of pathway from these 4 pathways here, and then the K2 is following which type of pathway from these 4 different pathways, after that only we can analyze the rate law of that particular nucleophilic substitution reaction, right? So basically in this lecture here we are talking about the nucleophilic substitution in case of square planar complexes, and we have seen that if the substitution of the complex, I mean the square planar complex, is taking place with some Y ligand or the Y entering nucleophile, we will be having this type of rate law equation, right? But in order to analyze this rate law equation here, we should know that the values of K1 and the K2 corresponds to which pathway. Is it the associative or the dissociative, or is it the interchange associative, or whether this K1 and the K2 values are following the interchange dissociative type of pathway. Only then for that nucleophilic substitution in case of the square planar complexes, we can analyze the rate law equation, right? So now let us first of all discuss about these different pathways here. So before that, you can see whatever I have just told you, that the K1 and the K2 rate constants, they corresponds to which of these 4 different pathways. It is very important to understand this thing first, okay? And now let us have a look on these different pathways. So you can see here, this is our starting square planar complex. Let me complete the geometry of this starting complex molecule in this way here, such that it is now reacting with this Y ligand here, which is the entering nucleophile, and this X ligand will be going out of the system after the attack of this Y nucleophile, right? Now we may have 4 different kinds of pathways as we have just discussed on the previous slide. The first pathway may be what, that the platinum and the Y bond is formed first. I mean when this thing will be reacting with this, such that the substitution of the X will be taking place with this Y here. We can have 4 different kinds of pathways. The first pathway will be like what, that before the platinum and X bond breaks, I mean before this bond breaks here, the Y will result in the formation of a bond with the platinum or the central metal line, okay? So you can see from here, the platinum and the Y bond is formed first before the platinum and the X bond begins to break, right? So we may have this first kind of pathway, and after that the second possibility may be what, that the platinum and the X bond, I mean this bond here, it is fully broken before the platinum and the Y bond begins to form, right? So once again, we are talking about the reaction in between this complex here and the entering nucleophile. So this was the first possibility. The second possibility can be what? That before the formation of the bond in between the Y, I mean the entering nucleophile, and our metal ion, before this bond formation takes place here, what happens is that the platinum and the leaving ligand bond is fully broken, right? So this is the second possibility here. Okay, we do have two more possibilities. The third possibility is what? That the platinum and the X bond, I mean this bond here, it begins to break before the platinum and the Y bond is fully formed. I mean this bond here, right? So what will happen in the third possibility? That this bond here we are talking about, this bond will begin to break here before the platinum and the Y bond is fully formed, right? But the difference is what here? That the bond making will be more important here in this third possibility here, right? So as compared to this bond breaking, the bond making will be more significant, right? And now let us have a look on the fourth and the last possibility, which is like what? That the platinum and the Y bond, it begins to form. I mean this bond here, it will begin to form before the platinum and the X bond is fully broken, right? Before this platinum and the X bond, I mean this bond here is fully broken, what will happen is that the platinum and the Y bond, it will begin to form, and this is the fourth possibility. But how it is different from the third possibility here? That in this case, instead of the bond making, the bond breaking, I mean this bond breaking will be more significant here, right? So upon the reaction, I mean the nucleophilic substitution reaction of this complex here with the entering nucleophile, we may have these four kinds of possibilities depending upon the priority of the formation as well as the breaking of different kinds of bonds here, right? And let me tell you that the first possibility is nothing, it is known as the associative type of reaction or the associative pathway. And then the second possibility is what? It is the dissociative type of reaction, or let us say the pathway. And the third possibility is what? It is known as the interchange associative, and the last one is known as the interchange dissociative type of pathway, right? So if we are considering the nucleophilic substitution reaction of this square planar complex with this Y entering nucleophile, we can have these four different kinds of pathways. And in order to analyze the rate law equation, it is very important to find out first that what type of pathway this reaction is following here, and only after that we can analyze this rate law equation here in terms of K1 and K2, right? And after that, let me give you a basic idea for that same reaction we are talking about from the beginning in this lecture. And we know that for this reaction in which the X is going out and Y is coming inside the complex, resulting in the formation of this kind of molecule here, the rate law is what it is? K1 multiplied by PT L2 Tx, and K2 multiplied by the concentration of the starting complex molecule multiplied by the concentration of the Y ligand here, right? And now this nucleophilic reaction can have either one pathway out of those four pathways, or it can also have a combination of two or more pathways, right? What I'm trying to say is that this reaction here, this nucleophilic substitution here, it can either have associative, dissociative, interchange associative or interchange dissociative kind of pathway, any one of them, or even it can have a combination of two or three different pathways. But how we can find out that what kind of pathway this reaction here is following? It can be done with the help of the values of the K1 and K2 here, right? So basically with the help of these K1 and the K2 values, we will try to find out the reaction pathway, whether it is actually an associative type of pathway, or it is a dissociative type of pathway, or whether it is an interchange associative or interchange dissociative kind of pathway. Okay, so now let us have a look that how from the values of the K1 and the K2 we can find out what kind of pathway this reaction is actually following, so that we can finally analyze our rate law equation, right? So this whole lecture is all about this thing. Okay, so now you can see that from the rate law equation, which is actually this here, the K2 value actually indicates that both, the concentration of the starting complex material as well as that of the entering nucleophile, they are important for the reaction. Okay, from this term here, it is very clear that K2 depends upon the concentration of the starting complex as well as that of the entering nucleophile, clearly suggesting that this kind of species formation will be the rate determining step in this reaction here. Once again, I repeat that from this part of the rate law, it is very clear that because the K2 values indicates that both the concentration of the complex material, the starting complex material, as well as that of the entering nucleophile, they are important for this reaction. So this clearly indicates that it is an associative type of pathway, and the formation of this complex here or this intermediate here is actually the rate determining step, right? And now let us talk about the K1 rate constant here, which says that, or which indicates that only the complex, the starting complex molecule, which is this here, only this is important for the reaction, suggesting a dissociative kind of pathway, right? So now why we are calling it as a dissociative pathway, because you can see here that the values of K1 are actually dependent on only the concentration of the starting molecule, and they are independent of the values of Y, so that we are not considering Y here in this case, we are not considering that, right? So the K1 indicates that only the concentration of this thing, this complex here is important, and the formation of this 3 coordinated state here is important because it is the rate determining step here, in which the X is completely dissociating from the rest of the molecule, and this is the rate determining step here, indicating a dissociative kind of pathway. Okay, but I want to tell you here that even this is actually what it is, an associative type of pathway. The reason is what, that the solvent is playing an important role in this reaction. Okay, so what happens is that before the formation of this kind of 3 coordinated intermediate, this solvent plays an important role in this reaction, and it coordinates itself with the starting complex molecule, this thing here. Okay, so what I'm trying to say is that the role of the solvent is actually making this pathway as an associative type of pathway. You can see here that the solvent molecule is coordinating itself with the starting complex molecule in the same way as the entering nucleophile was associating itself with the starting complex molecule in case of the K2 type of rate constant, right? So the only difference here is that in K2 we are having an associative type of pathway, and Y is present in this form. The formation of this thing or this species here is the rate determining step, right? And as far as the K1 is concerned, the K1 rate constant is concerned, it is this species here, the formation of this species, which is the rate determining step, and such that the rate will be dependent upon the concentration of the starting complex molecule as well as that of the concentration of the solvent here, right? So clearly indicating that it is also an associative type of pathway. At one look, it seems that it is a dissociative type of pathway, but it is actually not, right? So that I can write here that the formation of this species here is the rate determining step, and it is not dissociative kind of pathway. It is actually an associative type of pathway, because in the same way here as Y is coordinating here, resulting in the formation of a 5 coordinated species here, that is the rate determining step. In the same way, solvent is associating itself or coordinating with the starting complex here, resulting in the formation of a similar type of 5 coordinated species here. Okay, so both the K1, this here, as well as the K2, they are indicating that it is an associative type of pathway, right? So finally, I can say that for this nucleophilic substitution reaction in which Y is entering here and X is going out of the system, the rate law is what it is equal to this thing here, in which both the K1 as well as the K2 here indicate that it is an associative kind of pathway, right? Now, in this case, there is no doubt, because the K2 is suggesting that both the concentration of this thing as well as the Y, they are important, clearly indicating an associative kind of pathway. But on looking here at the values of K1, it seems that the concentration of only this thing is important, indicating a dissociative kind of pathway. But at the same time, we are adding here that the solvent plays an important role, such that the K1 here, I mean this K1 here is what? This is equal to K dash multiplied by the concentration of the solvent that is also present in large excess, right? So that it is also a constant here. This is a constant here, multiply by the concentration of the solvent in large excess, that is also a constant here, such that constant multiplied by constant will come out to be constant K1 here, right? So because it is dependent upon the concentration of this thing as well as on this thing, resulting in the formation of this kind of 5 coordinated state here, in which the solvent molecule was present in this way. So it is also an associative kind of pathway, and this is also an associative type of pathway. So finally we can say here that this reaction is actually following an associative type of nucleophilic substitution reaction. Okay, so this is all about this lecture here. Thank you so much.